Hmm. Hi guys, can you guys hear me? Hmm. Hey Aaron, can you hear me?
Yes.
Okay, awesome. Thank you. Hmm. Let's see. Hmm. I don't know. Okay, guys, if everybody can hear me, I'm going to go ahead and get started here. Um, I don't know if you guys had a chance to um, look at the Blackboard screen, but we have the syllabus up on the screen. I'm sorry, on the screen. I hope you can see it. It's also on the Blackboard. Um, Guys, can you ask somebody to give me a shout out that you guys can hear me okay and see the syllabus? Sorry, it's the first Zoom of the
Yeah,
semester.
we
So,
hear you.
okay, and can you see the syllabus?
Yeah.
Yep. Yes.
Awesome. Thank you, guys. Um, let's see. So I don't know what it says in the catalog, but we're going to have the course be synchronous. And so I wanted to jump ahead to the grading and try to explain it. So we're going to have, I think we're going to end up with about 7 quizzes, in-class quizzes. They're going to be 30 minutes each. And so that's 56% of the grade. So before, last semester we had, I think we had a couple of midterms and a final, but I felt like given that we were online, I wanted to kind of spread, instead of having just 2 midterms and you could get into trouble if you fell behind and got hammered on one, kind of sort of divided up into a bunch of in-class quizzes. So in terms of the schedule, we're going to have 7 quizzes. And the way it's going to work is, I guess at the beginning of the class, I'll put up the quiz. You guys will have 30 minutes to work on. It'll be like 1 or 2 problems, and you guys have like 30 minutes to complete them and send me the what you have. And if if you are, I'm a pretty flexible guy. If you guys, for some reason, need to miss a quiz, miss that class, you can go ahead and let me know ahead of time and we can work something out. So in terms of the class, we're going to be working on microelectronics, and I'll talk a little bit about that, have some slides just to give you guys a sort of a big picture. But the idea is that, hopefully you guys have had some circuit classes previously. So maybe hopefully you're familiar with, doing Kirchhoff's current law, Kirchhoff's voltage law. Those are both important. And, I don't know if we're going to get into Thevenin equivalents or things like that, but hopefully you've had that experience. And then hopefully you've had the experience of analyzing RLC circuits, mostly RC. I think we might end up, I don't know if we're going to have any L's, but I don't think we will. No, I think we will have some L's in there too. So, those are the experiences you've had with, I guess I'd call those linear circuits, but it's a situation where, you really don't have nonlinearities. If you look at a resistor, an inductor, a capacitor, they're basically symmetric devices, no matter how you hook them up, and they're two-port devices. Microelectronics are the other 99.999% of the actual devices you get in electronics. We're going to start with diodes, which are
Now.
Go ahead, sorry. Did somebody say something? Anyway, so diodes are, sort of switches, one directional. They turn on in one direction, off in another. And then we'll also talk about bipolar and MOS transistors. And those are three-terminal devices where one terminal is used to control the device, and the signal goes sort of through the other two terminals. And depending on how you use those, you can get different functionality. So with these kind of devices, you can get things like voltage regulators, you can get voltage upshifters, downshifters, you can get amplifier circuits, you can get logic circuits. So basically, the world really opens up with microelectronics. So, the main thing, this is kind of a starting point in terms of circuit design. I mean, I think previously your linear circuits were good. Here's where we really look at practical circuits. So hopefully this will be your introduction to practical circuits.
Professor?
Yes.
You're cutting in and out like a lot right now.
Oh, really? Huh.
Yeah.
You know what? My internet connection may be crummy. Let me, give me 1 second. Let me see if I can log in with my iPad that's got an LTE on it.
Okay.
1 second. Shoot. Hey guys, I'm having a hard time with the, it's still pretty bad?
Yeah, it is for me. Does anyone else having issues?
Yeah, it cuts off in and out. Yeah.
Yeah, thank you.
Okay, let me do try one other thing. Hold on. This is the curse of living in the boondocks, guys. Personal hotspot. Let me try my hotspot. Okay, guys, are you still there?
Yeah, we're still here.
Yes,
Yeah, we're still here.
Is this any better?
I think so. So
It
far.
might be. So far, so good.
Okay,
Yeah,
so
seems
this is just my hotspot.
Okay.
Okay, so far so good?
Yeah, we'll just let you know if it happens again.
Okay, awesome. Thank you so much. Okay, so anyway, so I have the objectives here. So one is get sort of a big picture idea on what microelectronics are. You know, I think at least my personal sort of first experience with so-called, you know, circuit design classes wasn't really that positive, because, you know, I couldn't really get an idea, you know, again, the circuits with, you know, these circuits of resistors, inductors, capacitors, it's not clear what good these things do. So hopefully in this class, you're going to start getting a picture of some circuits that are more realistic, and it's going to prepare you to handle, you know, stuff in the lab and more advanced classes like chip design, et cetera, whichever direction you want to go. So we're going to start with semiconductor physics, and I'm going to go really light on that. The reason we're looking at semiconductor physics is because these microelectronic devices are made out of semiconductors. So you need to understand it a little bit, you know, how you can use a silicon, you know, semiconductor to create diodes, transistors, et cetera. And the first structure that we learn how to make is a PN junction. And we'll talk about what that means, how you can get a diode from a PN junction. And then we'll talk about the concept of using what we call small signal model. That's another concept that I didn't really understand when I was an undergrad too well. And the idea is that these nonlinear devices, like a diode, has a exponential characteristics between voltage and current. And that what that does is, if you just want to plug in that exponential into complex circuits, it gives you a lot of complex equations that are difficult to solve. So what you do is you only operate the circuits in a very small range of the diode or the transistors, and you use linear approximations to make the circuits more understandable and be able to analyze them. And then with the diode and this linear models, et cetera, we'll show how we can build you know, rectifiers, limiters, and probably like a voltage regulator. And these are all the circuits you'll be using in labs, at work, if you're building boards, et cetera, building any kind of hardware, you'll be using that. Then we're going to get into bipolar transistors, and it's going to have to be really basic. I mean, I think to get a really good view of microelectronics, I think you need at least 2 semesters. This is a 1 semester class, so we're going to be just sort of touching on amplifiers, and then we're going to move to MOS transistors, how they work, and then MOS amplifiers. Okay. The book for the class, the text is Fundamentals of Microelectronics, 2nd edition, and I think you should buy that or get a PDF or something, whatever you guys are going to do. Because, you know, one of the main, so this is, by the way, my 2nd semester teaching a class. And I'll talk a little bit about, you know, my background, you know, what I do for a living, et cetera, the rest of the time. But I think what I didn't emphasize enough in the previous semester was how many examples you guys have to go through to really be successful in this class. You're going to have to basically solve a lot of problems. A lot has to do with getting these circuit problems and doing the analysis. So that's, you need a lot of practice. And so, and you know, I'm going to be putting up the homework suggestions on what you guys should be doing. I'm going to be putting up the homework solutions, but I'm not going to be grading the homework. So you don't need to hand in the homeworks, but you know, I think to do well on the quizzes, you really need to do the homeworks. That's sort of my plan, is to make sure those are linked. And of course, the final. Another thing that's optional for you guys, but it's, you know, pretty cool device, is Spice. I don't know if you guys have used Spice before, but it's a simulation tool. It's pretty universal for simulating electronic circuits. And the cool thing about it is you can actually, you know, I have a tutorial online that I can link to you guys, but you can actually use it to kind of check on your hand calculations. So for the quizzes, the homework problems, etc., you're going to be doing hand calculations. But the nice thing is you can use Spice to like verify that you're on the right path there. Okay, in terms of, you know, the technical requirements, I think this is all formulaic. You know, you need a computer. Classes are going to be online. I'm recording the classes and I'm going to put them up. Probably, you know, last semester I was doing it on YouTube, which worked out fine, and just send you guys a link to it so you can have it. You can check it out later. Like I mentioned, you know, you'll need access to internet, your computer, etc., during the class, because we'll have those quizzes. And then, you know, I don't know if you guys are going to want to print them out real quick, or just, you know, handwrite them, take some pictures with your phone, or, you know, if you have an iPad or Surface or something like that, you can just do it real time. So again, grading is 56%, and there'll be 7 quizzes. So 1 every 2 weeks, and 44% for the final. You know, academic integrity and being neat or whatever, I don't know. This is all, you know, you guys, I think you guys know this stuff better than I do. All right. Any questions? Oh, and then one more thing, sorry. So my office hours are also going to be Zoom. I put them on Mondays and Fridays at 4 to 5 p.m. We'll see how well that works. If I don't know if everybody is as in the US who's taken a class, at least, you know, I'm teaching a VLSI class, and at least one of the students was going to be dialing in from Hong Kong. So anyway, if these office hours, for whatever reason, you guys, or somebody's in a different time zone, I'm happy to work with you guys if you need to set up a separate meeting and so on. Okay, so any questions about that so far? Okay, so in terms of, let me get to the Blackboard. Let's see. No, it's going really slow here. This is my hotspot. Sorry, guys. Well, while that's doing its thing, I'll talk a little bit about my background. So, you know, I'm not from an academic background. I have a, I mean, I got a PhD in electrical engineering, but after I graduated, I went into industry. So I got my PhD from UC San Diego, and again in electrical engineering and applied physics. And then afterwards, I went and worked in JPL, Jet Propulsion Lab here in Pasadena. That's sort of when I moved to LA. And then I was really interested in doing startups, so doing entrepreneurial things. And so the reason I joined JPL is because there was a group there that was working on a pretty new area that looked really promising. And indeed, I got pretty lucky because it did really, the areas really did do well. It's basically camera chips, CMOS image sensors that are now being used in your cell phones, computers, et cetera. So, it turned from a $0 market in 94, I think is when I joined the JPL, till now it's, I think, $12-13 billion market worldwide in that time. And I've been pretty much in that business since JPL. So went to JPL, then my boss at JPL spun off a company off of the work we were doing at JPL. I joined that. That was bought by Micron Semiconductor, was a semiconductor company in 2001. And after it was acquired, I wasn't really interested in working for a big company. So I left that company who acquired us, and me and a friend of mine, we started our own company in 2001. And then we ended up selling that company in 2018 and to a Fortune 500 company. And so since then, for about a year and a half, I was still running the company. And since then, since beginning of June, now I'm kind of semi-retired. I'm working for that. So my title is President Emeritus. So I'm helping him with business development and marketing. And then, I'm doing consulting work for some other companies and trying to come up with ideas to start sort of the next company or decide to retire. So we'll see what happens, if my wife will let me. And then, one of the big things was during this time, it was a pretty successful exit we had in 2018. So I would say when we sold the company, I think we were 45 people, and about 10 people, I'm very proud of this, at least 10 out of the 45 became millionaires as part of that exit. And I think basically everybody in the company made, the least of it was, being able to buy a nice car or something like that. So everybody, I feel like I'm very happy with the way we exited in terms of what happened to our team, to our employees. And a big part of that were Cal Poly graduates. So, when we started, there was a team of us that we're working with together before, and that was sort of a core team of 3, 4, 5 people that sort of gradually joined us from, experienced people. The rest of the time, we were recruiting straight out of school, and one of our great recruiting pipelines was Dr. Olson from Cal Poly, who I know from my UC San Diego days. We went to school together, and she sent us some really great students who basically helped build a company. And so I felt like, once we sold the company, et cetera, I felt like it was something I wanted to do, is to come back to and sort of teach in Cal Poly, teach you guys what I know, I think the thing I bring to it maybe a little bit, you won't see it as much in this class, I think the guys in the VLSI class see a little bit more of it because that's a senior level class. But I'm hoping I'm bringing kind of a more of an industry angle in terms of what you guys will see when you graduate and go to work. And so more industry, less academic sort of background. So that's my background. Let's see. In terms of the schedule, let's see, what do I have? Any questions, guys, about my background, what I've been up to? Feel free to jump in. Okay, so we got the syllabus.
What company did you create?
It's actually still running under the same brand. It's called Forza Silicon, Forza space Silicon. And my LinkedIn is actually on the Blackboard. I was actually kind of trying to get to it. So there's information on the company, and we were bought by a multi-billion-dollar company called Amitech, which owns like 40, 50 companies kind of like us, and sort of as a conglomerate.
Oh, wow.
Yeah. Okay, so anyway, here's the course schedule. Okay, so I just have a list here. I only put some details on for the first few weeks, and hopefully I'm going to go not hopefully, I will populate the rest of this better as we go. But the first quiz. Well, okay. So I don't want to. You're going to have one quiz 0 next Tuesday. It won't be graded. It's just so that I get a feel for where you guys are with your understanding of Kirchhoff's current and voltage laws. So I know it sort of gives you guys a flavor of what the quizzes look like. But it won't be graded, but I just want to give it to you guys so I get a feel for where, if anybody needs help. After that, our first real quiz will be on September 3rd. Maybe a lecture before, maybe a lecture after. I'll let you guys know if the time gets moved, depending on how fast we move. Basically what we're going to be by that time, we would have looked a little bit at semiconductor physics and PN junctions, and how the PN junctions create a diode. So, and then I have a list of problems here. What I tried to do in the reading is I'm going to try to not have it, like here I have skip Thevenin and Norton equivalents in chapter 1. Try to not make you guys read everything, but like chapter 2, I think you basically have to read the entire text, and then not do every problem. I'm trying to down select the number of problems, but as you can see, it's still a pretty significant number. I don't know, maybe 20 problems here, or 17 or 18 or something. And then I'm going to have solutions for those. Anything else I want to say here? No.
Lester, I have a quick question.
Yeah.
This schedule, I tried pulling it up and it didn't let me. It said the format wasn't allowed. I thought it was Microsoft Word, but I wasn't able to open it.
Okay. Thanks for letting me know that. I'll see if there's another way for me to put it up there.
Thank you. I appreciate that.
Thanks.
Were you able to download the file though?
No, I wasn't able to access it and get it all.
No, actually, it doesn't let you. Yeah, I also tried to, but I couldn't.
For me, it downloaded, but I had to open it through a notepad, and it looks just like the professor's, if that helps.
Yeah, mine just opened fine with Microsoft Word. Just download it, open the folder, right click, and just click open with and choose Microsoft Word.
Okay, so let's see. Let me do this.
I got it to work. Someone said to do the open it with Word separately, and it worked.
Great. So, guys, what I was gonna do is, let's see, again, if I can do this full time. So I was gonna get, dum, 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 dum. There we go. I just wanted to just go through down this list and you know, have you guys say a few things. Well, like before I get into that, let me lead you guys to what are, I'm gonna have you guys do an assignment for this weekend. And this is gonna be your assignment. So everybody needs to do this, is everybody needs to send me an email with your, as just as a student, your 3 biggest strengths as a student, your 3 weakest points as a student. Okay. So, I mean, in terms of the weak points, it may be that, I don't know, you're working 40 hours a week or something, and, or I don't know, you're taking care of your parents, or, you know, basically like whatever is sort of holding you back as a student. So 3 biggest strengths, 3 weakest points. Okay. And then I'd like you guys to tell me what grade you are expecting in the class. Okay. And if that grade is anything else than an A, I'd like you guys to tell me why you don't think you can get an A in the class. Okay. And it could be legitimate. Look, you know, maybe again, you have other obligations, maybe you have a huge class load, whatever. But so first, I'd like you guys to think about why you shouldn't be getting an A in the class. So mentally, I want to take you guys to getting an A in the class, all of you. But if you don't think you can get an A, I want you guys to tell me what grade you're expecting in the class. And, you know, if it's not an A, at least I have a feel for it. And as the class progresses, if I feel like you're dipping below that, or you're in that kind of a trajectory, I can, you know, pay special attention. We can work together to bring you back to the grade you guys need to get. Okay. So 3 weakest points, 3 strongest points, and the grade. And if it's not an A, why you don't think it's an A. Okay. So those are your things for the weekend. So the rest of today, I was just going to go again through the class roster and have you guys tell me a little about maybe your background, what you want to do out of the class, whatever, to introduce yourself to the rest of the class. You know, we're all online, so hopefully, you know, I'm hoping that you guys will be able to work with each other, you know, not copy quizzes, et cetera, final, but it's nice to work together and learn together. So sort of introducing to each other. So also, if I'm butchering your names, you can let me know. So let's see, I'll just start from the top. Daniel Acosta. Is Daniel?
I'm here. Yes.
Hey, Daniel.
Daniel Costa. I'm a sophomore, and I mean, obviously, electrical engineering major.
Mm-hmm.
I am really excited for this class and see how far I can go with all of this. Yeah.
Okay, thanks, Daniel. Let's see, Manuel Barrera.
Hi everyone. Hi Professor.
Hi.
My major is electrical engineering. I'm a transfer student from Sonoma College, and I'm so excited to see what I can learn from this class, of course.
Okay, great, thanks. You said Sonoma College?
Sanana College.
Okay, great, thanks. Let's see, I have Jaden Bautista.
Yeah, Jaden's fine. It's my second year here,
Uh-huh.
computer engineer. And yeah, I'm also excited to be in the class, see what I can learn.
Great. Ignacio Chirino. Okay. Hai Chow.
Hi everyone. My name is Aicho. I'm a computer engineer. This is my second year in Cal Poly, and I'm really excited to learn more stuff. I actually checked this class before, but unfortunately I have to drop it. Hopefully I can get something out of this class. Thank you.
Okay, great. Okay, let's see, William Kordoff. Okay, William. Samuel Escobar.
I believe he's on the chat. He said his mic isn't working.
Okay,
Hi,
yeah.
I'm Samuel.
Hi, Sam.
Hi, my name is Samuel Escobar. I'm actually a transfer student from Santa Monica College. It's my second year here. I'm an electrical engineer, and I'm excited and curious of what it is I'm going to be learning so far about these components that I'll be using in the future.
Great. Hi, Samuel. So I have Isabel Magdalena Garcia.
Hello, I'm Isabel. I'm a double E major, and this is my third year at Cal Poly, and I'm excited for this class.
Great. Thanks, Isabel. Gabriel Garcia.
Hi, you can call me Gabe, I guess. I'm excited to take this class. I'm a second year electrical engineering major, and I'm just excited to suck up as much information as I can, get out there into the industry.
Great, great. Nicholas Garcia.
Hi, everyone. Just to begin, I think Ignacio put something in the chat just to let you know. But my name is Nicholas Garcia. I am a second year here at Cal Poly Pomona. My major is both electrical and computer engineering. I'm double majoring. And I don't know too much about microelectric circuits, but I look forward to learning more about them.
Great. Gabriel Howard Ron.
She's on the chat again.
Okay. Okay. Gabe, so chat. Okay, Gabe. Chat. All right. Let's see. Let me see if I can read the chat things. How do I do this? No. Man, I got to remember how to use Zoom. So yeah, you don't use it, you lose it. Jason Hoyne.
Yeah. I'm Jason, and I'm a third year computer engineering student.
Okay.
I'm really excited to be in this class, and I hope I can get along with everyone else here.
Okay. Jason, can you say your last name for me?
Yeah, it's Huyn.
Hoyne.
Yes.
Thanks.
Yeah,
Elizabeth.
no problem.
Okay, thanks, Jason. Elizabeth Huyn. Okay. Let's see. Daniel Curry.
Hello, it's Corey. Hi
Corey.
guys, my name is Daniel. I'm a computer engineer major, transfer student, but it's my second year at Cal Poly. And I'm just looking forward to learning some more about everything in the industry. So
great.
Yeah.
I like how we have a lot of computer engineers. I think I'll try to link more of what we're doing to computer engineering. Hopefully, it'll be interesting. So
Hey, that's pretty cool.
yeah, Xavi or Xavier Luna.
It's Xavier.
Xavier, sorry, Xavier.
Yeah. Okay. My name's Xavier Luna. I'm a second year at TPP, and my major is computer engineering, and I'm just excited for what the class has to offer.
Great. Juan Manriquez, sorry.
That's fine. Hello, everybody. My name is Juan Manriquez. I'm a computer engineering major, and I recently transferred in from East Los Angeles College this first semester. And actually, I'm very excited for this class because my favorite component is a transistor. I love transistors. I'm like, how do they make the logic gates? And then it's like the old transistor. So that's why I'm excited.
Great. Thanks, Juan. What do I do with this one? Let's see. Jorge Medina? Did I get that?
George is fine.
Can you pronounce it for me?
You can just say George. It's fine.
George. Okay. So would it be Jorge in sort of like a Spanish pronunciation?
Oh yeah.
Yeah.
It,
okay. Yeah.
Well,
Sorry.
my name is George Medina. I'm a second year at Cal Poly. I'm an electrical engineering major, and I'm just excited to see what I can learn in this class.
Okay. Thanks, George. Aaron Pacheco.
Yes. So I'm Aaron Pacheco. I'm a computer engineer, and I just had a lot of fun working with computers in my past. So I'm really looking forward to expanding my knowledge.
Okay. Thanks, Aaron. Eileen Paces.
Hello, my name is Eileen Paces. I'm a third year computer engineer, and I'm excited to learn and expand my current knowledge for this class.
Thanks, Eileen. So we have Jacob or Jacob Reyes.
Yeah, hi. My name's Jacob Reyes. I'm a transfer student, but this is my second year at Cal Poly, and I'm just excited to learn more.
Great. Thanks, Jacob. Nathaniel Ruiz.
Yeah, this is Nathaniel Ruiz. I'm a transfer student from Mount Sac, second year here at Cal Poly. I actually am an automation worker for IQC, so this will hopefully expand my knowledge with micro and stuff like that.
Cool, awesome. Adrian Sachs.
Hello, everyone. My name is Adrian. I just transferred here from Mount Sac this semester, and I'm a ECE major, and I'm pretty excited to start learning about transistors and microelectronics.
Great. Thanks, Adrian. Cesar Santiago Sanchez.
Hello, I'm an electrical engineer major, and I'm pretty excited to learn new things in this class.
Great, thanks, Cesar. Absalon Soto.
Hello, everybody. My name is Absalon. I'm majoring in electrical engineering. I'm excited. This is my first semester Cal Poly, transferring from Mount Sac, and excited to start a new chapter in my life.
Great. Thanks. Fahad Sayed.
Hi, my name is Fahad. This is my second year at Cal Poly. I'm an electrical engineering major. I'm just excited to be here as well.
Thanks, Fahad. Darian Tam.
Hi everyone. My name is Darian Tam. I'm a third year major. I'm a third year here at Cal Poly, and I'm a computer engineer major. I'm just excited to see what this class is in store.
Great, awesome. Thanks, Darian. Elvis Tang.
Hey guys, it's Elvis Tang. I'm a computer engineering major. I'm excited to see how this class, the components that I could learn in this class relates to what I want to do research in, which is virtual reality. Yeah, I want to see how the components would, I guess, relate to that. Yeah.
Cool. Javier Tapia.
Hello, I'm Javier Tapia. It's my third year here, computer engineering major, and I'm happy to see what I can learn from this class.
Awesome. Thanks, Javier. Amber Thomas.
Hi, everyone. I'm Amber. I am a third year, also electrical engineering, and I'm excited to be here. And also, I really like to work with people. So if anybody wants to take down my email address, I'll put it in the chat.
Great. Thanks, Amber. Darren Tran.
Hello, Darren Tran. I'm a computer engineering major, and I'm just ready to learn more about transistors.
Great. Wow. A lot of computer engineers. Raghav Vathawan.
Hi, I'm Raghav. I'm a third year here at Cal Poly. I'm an electrical engineering major, and like everyone else, I'm excited for this class and to see what we'll learn.
Great, thanks. Andrew Wong.
Hello, my name is Andrew. I'm a second year electrical engineering major. And yeah, just like everyone else, I'm excited to learn everything I can from this class.
Okay, great. Thanks, Andrew. Well, that was really good for me. I guess, you know, it seems like we have almost more computer engineers than electrical engineers in the class, which will be, you know, interesting. So I think that's a good mix. So let me do this. Let me just give you guys, I made, you know, it's sort of let me see here. So I can pull this up. Okay, so I made sort of an introductory slide deck for you guys just for today to, you know, tell you guys sort of at a background level what microelectronics is about. So, you know, and it really kind of comes from a computer perspective, I guess, you know, going down the history of where, you know, people were trying to build custom computers. And, you know, starting, this is sort of the first recorded or first agreed on computer, which is from, God, it's like, I guess, 190 years ago or something. And it was all made out of mechanical parts. And I think it basically multiplied. And, you know, just sort of gears, I think it was sort of the size of a refrigerator or something like that. And it cost 17,000 pounds of 190 years or whatever, 190 years ago, which I think I read somewhere there was, you know, $1 million+ for something that multiplied, okay? Then sort of fast forwarding to sort of World War II, you know, we've had the first electronic computer, and this was the ENIAC. So these are all kind of, who knows, but these are like historically accepted as the first and the first. So the first computer, which was mechanical, and then the first electronic computer. And this electronic computer was all from, you know, vacuum tubes. So it was not made from semiconductors. So vacuum tubes, you know, I don't really know much about them myself, but you basically do the same thing as you do with a transistor. You sort of control the flow of electrons, but they are physically large, you know, might be the size of, you know, some of the ones I've seen are kind of the size of, what would be, size of a cigar, say. I don't know if you guys are, got any smokers in the class. But, and, you know, because, you know, a lot of it, they couldn't, let me wait till and then come back to it. So anyway, this was the vacuum tubes. And so the first transistor was, came out of Bell Labs in 1948. And you can see that this is actually was made from germanium. And, you know, it's got, it just really, looks really cheesy here. They've got some wires soldered on to the gate and controlling it, etc. So that was the first transistor. And it was nice because it was made from a semiconductor. It didn't have these vacuum components. It could be made smaller as an individual device. But one of the real breakthrough, I think, came in when people started to put multiple transistors in the same substrate. So that's the so-called first integrated circuit. And so this one, you know, this is really sad, but it was the first one, 1966. It's a 3-input gate. You know, it doesn't do very much. It's a piece of, but you can see they've got, you know, if I count it up, 1, 2, 3, 4, 5, 6 transistors in the same substrate. And this is significant because when you have individual components, vacuum tubes, etc., and you're plugging individual components, you have some serious reliability issues. That's the main thing. Okay, you end up having a physically very large device. If you look at this, you know, ENIAC computer, it's basically the size of, you know, one of the labs in Cal Poly. And the reason it needs to be so big is because these vacuum tubes, you know, you got, each of them is the size of a cigar, and you need thousands and thousands and thousands of them to do something useful. So physically, they tend to be large. They tend to use up a lot of power, and the reliability is really poor. That means somebody constantly has to go through and replace these. You know, the transistor made from semiconductors, it was really cool. It could be physically smaller, it could be cheaper. But again, connecting these as individual components, you still had reliability and space issues. So the real you know, revolution in my mind came with the integrated circuit. And once it started, it was, you know, kept going and going. So the first you know, we started from this 3-input gate. The first microprocessor was in 71 with 1,000 transistors. An Intel chip. I think it was for a calculator, for a Japanese calculator maker. And you know, some of this stuff is old, but again, the Intel Pentium chip. You know, this was already in the millions of gates. And you know, of course, now we have chips that are, I think the new AMD chips are billions of gates. Okay, so this is the extent of where, you know, microelectronics is from a purely computer engineering approach. So all these are made from microelectronics, basically. These are, you know, collection of transistors, et cetera, for the most part. Okay, and this is all from this thing that is called Moore's Law, because the guy who came up with it was called Gordon Moore, and he was one of the founders of, and he was a CEO of Intel for a very long time. And he predicted that, you know, once they started building the integrated circuit, once they started putting more than one transistor in the same substrate, he realized that the number of transistors on a chip could double every 18 to 24 months, which is, it's doubling every 18 to 24 months. So it's kind of like, you know, the COVID spread or something like that. These are like exponential growths. It really takes off, and it's just amazing going from a few devices to, you know, doubling every 18 months. So this Moore's Law, again, I think it's something you guys might have heard from in the news, et cetera. It's slowed down significantly recently. You know, some people think it has flattened out. There's different reasons, you know, I'm not going to get into it now. But actually, maybe we can talk a little bit about it. But the main reason is, you know, power consumption is an issue, and just the cost of the factories to build these microprocessors are now in the, you know, $5 billion range. So, and every generation, they get more and more expensive. So right now, that these factories are, their names, or they're known by, what are we doing on time? 6:25. They're known by the minimum size of device that you can make in them. And so right now, the most aggressive ones are 5 nanometers. So that's 5 times 10 to the minus 9 meters, or whatever it is, 1/5 billionth of a meter, which is very, very small. And they're working on they're working on a 3 nanometer process, et cetera. So, as you can pack a lot of devices in there. So here's a example of Moore's law, and this is pretty old, but the line continues, and you can see this is a straight line on a log axis. Okay, meaning that this was his prediction about what the growth would be, and indeed, if you look at actual transistor counts, again, this is kind of old. From the mid 2000s, you were already at million. This is a million K, so it'd be at a billion transistors here at 2010, starting at 10,000 devices here in the 1980s, et cetera. 75, it would have been something like that, 10,000 devices, et cetera. So notice that this is a log scale, and this is a linear scale. So anything like this is just amazing. You can see how much stuff you can pack into a device, okay? And so when you look at what kind of devices this goes to, it's not just, computers, or, I think cell phones are really, smartphones are really sort of the thing that's moving the fastest. And it's got significant, most of what you have, I sort of break this down in the VLSI class, which is the other class I'm teaching. But I think I looked at an iPhone, which is, I think the iPhone 11, I think, sells for, let's say, $1,000, $1,200. So something that sells for $1,000, the bill of materials, that means the cost to Apple to put that phone together, to have a decent business, the bill of material needs to be about 1/3 the price, okay? So the bill of material for an iPhone 11 is something like $300, something like that, okay? So that's how much it costs Apple to put that thing together. And from that, it's sort of looking at the individual components and pricing it. About $250 of that is microelectronics in there. Okay, so what are those things? Well, sort of for the computer engineers in the class, and for the EEs, but I think the computer engineer is more interested in, the baseband chip, the controller. So that is a very large chip, a very large, again, multi-billion transistor chip. And it's made by companies like Apple itself makes its own chips. Qualcomm down in San Diego makes chips for a lot of the other cell phones. Those are called Snapdragon line of chips. I don't know if you're familiar with them or not, but if you're in the computer engineering business, you will become familiar with them. And so these are sort of the baseband control. And then for the EE guys there, it's sort of the rest of these things, which is analog baseband control, the RF radio frequency components that are going to be transmitting the signal and receiving it, and power management, et cetera. And these are, again, old numbers about the number of units of cell phones sold in the world, but there are multi 100 million cell phones, smartphones sold in the world. So you can just imagine how big this market is just from a cell phone perspective. You know, you have, I don't know how big the PC market is. I think it might be like 20, 30 million a year, something like that. And you can, you know, the PC, the microelectronics on the PC, obviously, you know, something that you can think of being, you know, a lot of the PCs made of microelectronics. And, you know, the next high volume thing is cars, automobiles. So even, you know, when you don't think about like a Tesla, which is really all sort of electronic car, even when you think of a regular non-hybrid gas car, still a significant amount of what's in the car in terms of the cost of the car, the volume, the weight, etc., is actually microelectronics, even for a gas car. It's all the stuff that communicates, controls the engine, controls the braking, controls the engine, etc. So it's, and you know, the next thing is, so this is all this stuff, you know, there's microelectronics everywhere you look, you know, your cameras, etc. But, you know, the next real explosion that people are expecting is in the so-called Internet of Things, IoT. And again, it's probably something you guys have heard about. And the idea there is that, you know, we're going to be, everything in the world is going to be connected to the internet. You know, your light bulbs, your fridge, your toaster, your, I don't know, shower head, everything. So the number of chips are going to be actually, even that size of that market is expected to be much bigger than any of these other markets. As you can imagine, if you'll have things in each place. So for example, we've had customers interested in putting sensors into a light bulb that, say, would count the number of people in the room and their location, et cetera, and basically either doing directional change for the light or, you know, dimming the light, et cetera. And so it sort of gives you an idea of where things are going. So microelectronics is just getting into more and more into every aspect of our lives. And, you know, people are projecting it to go into our clothing, into our bodies. Anyway, so so anyway, it's just something that's going to be everywhere. Okay, so let's dig in a little bit into some of the stuff that in the cell phone. So, you know, we talked about the transmitter and receiver of a cell phone, okay, which is an important part of where it's something easy to kind of describe, let's say, as something for the microelectronics. And so basically, you know, that's this very basic part of your cell phone operation, to have a microphone and then some black box, something that transmits that data, and a speaker that, you know, somehow you receive that data, that electromagnetic field, and translate it into something that you can hear. So if you look at the problem, or what this is doing, is that your voice as I'm speaking, so what's this microphone picking up my voice here, if you look at the frequency components of my voice, it's actually pretty low frequency. You know, you're looking at about, you know, 20 kilohertz of modulation of my voice, okay? So if you try to just hook this frequency up into a RF transmitter, so let's say if you just try to hook up the microphone to an RF transmitter, you're going to end up with a huge antenna. So if you guys have looked at, you've taken E&M classes, or maybe not, but basically you need the size of your antenna needs to be about a quarter of the wavelength of the frequency you're trying to transmit. So if you're trying to transmit something with a frequency of 20 kilohertz, you're going to end up with an antenna that's multi meters long. You can't put that into a cell phone, okay? So what people do is they do a so-called upconversion. So they multiply this voice data, but with a much higher frequency signal. Let's say, so that's the frequency, you know, did you hear about, you know, the GSM band is this frequency, I don't know, and then, you know, 5G is this other frequency. So that's the frequency that your data, in this example, the voice, gets multiplied. So this plus minus this carrier frequency is going to be up at several gigahertz. And then basically that ends up having the voice modulates that frequency. That ends up being your signal. And now you can go to an antenna that's, you know, that you can fit, you know, around your cell phone, say. You know, you're talking about an antenna that's several centimeters as opposed to tens of meters long. So that's, you know, an example of something that's a very important thing that needs to happen in your cell phone, just to have a voice call, okay? So now let's look at that. So these are the different components that you need. Sort of schematically, you have your microphone, then you need to have, you're multiplying this other carrier frequency. This A cos 2 pi FCT is basically this cosine waveform that you're multiplying by your microphone, okay? And that can transmit. And so you need an oscillator to generate this frequency. So you need something that creates a multi-gigahertz signal. This is an example of a microelectronic component. You need an amplifier that takes this very weak signal and boosts it to, you know, again, cell phone. You know, the downside of it is people are worried about holding this thing next to their head, because there's, when you're transmitting, you got multiple, at least multiple hundreds of milliwatts of RF power coming out of that. And you know, the microphone signal's nowhere near that amount of power. And you need like a power amplifier to juice that up and transmit it. Okay, so that's another example of microelectronics. And also this multiplying unit is also microelectronics, okay? And on the receiver side, what you have to do is have the same frequency oscillator here, you multiply it and down convert, okay? Basically you end up with these lobes, you basically get rid of them and you end up with the central frequency. And so again, the signal, by the time it gets to your receiver, whoever's listening to you, that signal has traveled from your cell phone to some cell phone tower, and it's gotten back, being transmitted back to your cell phone. So although you sent out multiple hundreds of milliwatts, it's coming like maybe in the microwatts coming back to your cell phone. So what you need, something to amplify that signal so it becomes usable. And that's a low noise amplifier, because it needs to be low noise to be able to accurately amplify a very small signal. Again, you need the oscillator multiplier, you need the low pass filter, and then you need to be able to have an amplifier. You know, the typical speaker, the input impedance is pretty low. It's, you know, in the tens or hundreds of ohms. That's difficult to drive. And so you need an amplifier to do that. And these are all examples. So everything here between the, you know, the antenna and speaker is all microelectronics. And same here, between the microphone and the antenna, it's all microelectronics. And this is why, and you know, you can go repeatedly through your cell phone and see the same thing. And that's why the dollar content of what's microelectronics in your cell phone is such a big part of it. Repeatedly everything in the middle, all the stuff that's doing the smart stuff is microelectronics. Okay. So now let's look at how this is important for the computer engineers amongst us. So as where I don't know how much you guys are, some of you guys are second year. I don't know the curriculum background at Cal Poly, but when you look at the digital signals, this is in terms of time, and you have zeros and ones, etc. When things were slow, ones and zeros look like this. When you put it on your oscilloscope, yeah, they look like square waves, zeros and ones. Let's say it's 0 and 3.3 volts or whatever, 0 and 1 volt, etc. But as you get into multi-gigahertz digital signals, that's the signal frequencies in your cell phone, in your computer, microelectronics, etc. Things don't look so, at that level, things don't look so binary anymore. You have signals that are distorted, and you're going to have to treat them more and more like an analog signal. And again, this is something we see in the VLSI class, but it kind of gives you guys an idea of where computer engineering looks at microelectronics, understanding how transistors work, because you need to understand what your circuits are going to do at these kind of very high frequencies that you need to operate on, especially when things break. When you you design a chip, or somebody else has designed a chip, now it's not working, or it's not working at some temperature, or it's not working under some voltage supply level or something. You really need to have this kind of microelectronic knowledge to be able to go debug that digital circuit to understand what's wrong. So, okay, guys, so this is, I think we're at an end here for our first class. So again, I think you guys may have mixed luck with the course schedule, but I'll put it up. I'll try to put it up on the Blackboard in some other mode in case somebody wasn't able to get it. And then don't forget your assignment for the weekend. So 3 biggest strengths, 3 biggest weaknesses, all just as a student, and what your expectation is for a grade in the class. And if it's not an A, an explanation for why not. And it's okay, I'm not trying to browbeat you or say you need to get an A in this class. If for whatever legitimate reason you're okay with some other grade, I'd like to know it, and then sort of use that to make sure we track your progress. Any question from anybody?
You said you wanted us to email this to you?
Yes, please.
Okay. And the discussion part, is that also another thing we have to do?
In terms of what's the discussion?
In Blackboard, there's the discussion board where we have to introduce ourselves.
No, actually, I think just send me the email.
Okay.
Yeah. Any other questions, guys?
I just had a small one.
Uh-huh.
VLSI, very large, without, what's the main use of that one? Is it for computer CPUs and stuff like that, or is there another application?
Sorry, can you say that, the first part of your question again? Sorry.
Oh, sorry, for VLSI, so very large scale integrated circuits.
Uh-huh.
So their main application, are they for like computer chips, or is there another application for them?
They're for computer chips, cell phone chips, automotive. So anything that's a microprocessor is VLSI. So if you're having it do anything other than an analog functionality or something like that, it's going to end up being in the probably hundreds of millions of transistors. It's almost, I think it might be really hard to buy something that that has less transistors than that. You know, and another thing that is really VLSI, but people don't call it that, or FPGAs, field programmable gate arrays. I don't know if you've used those, but you know, these parts from Xilinx, Altera, that's used in a big part of lots of markets. Those are also have hundreds of millions of transistors in them. That'd be VLSI.
Thank you.
Sure. Okay, guys, any other questions? Okay, guys, so have a great weekend, and looking forward to working with you guys in the class.
Actually, I have one more question.
Sure, go ahead.
For some of the quizzes, can we use digital writing, like on my iPad?
Sure. Yep.
Okay,
Yep.
just.
And all the quizzes are, you know, obviously open book, open internet, open everything, except, you know, not open discussion with other students or other people, and you have that, you know, 30-minute time limitation. Okay, guys, have a great weekend.
Thank you.
Thanks,
Thank
Professor.
you.
Have a good one.
Bye.
Have a good weekend, Professor.
Thanks, you too. Bye.